I'm going to wait a little bit and let people roll into the webinar room from our participants. But for those that are already there, welcome to GBO Community Zoom. Okay, it's 1:01 by my computer clock. We'll go ahead and get started. So welcome everybody to the community Zoom at the GBO. Jim normally gives the observatory summary or update at the beginning. I'll just say a few words on that front. The upcoming proposal call will be August, or the first Wednesday in August. I think it's August 2nd. That will be when the proposals are due. The call will go out the end of next week, basically. So we encourage folks to put it in your proposals, start thinking about what you would like to do with the GBT. And I'll go ahead and introduce our speaker. Our speaker is Ryan Lynch. He's staff scientist here at the Green Bank Observatory. And he's going to be going over an update of the Cyclic Spectroscopy software project that has been ongoing at the GBT to help improve pulsar timing and sensitivity, basically. So if you have questions, put them in the Q&A box at the bottom, and then we'll go over them at the end. So Ryan, the floor is yours. So go ahead and take the screen and share when you're ready.
Thanks, Dave. Thanks everyone for joining. Hopefully everyone can see my screen okay. There's no annoying Zoom black boxes or anything like that anywhere.
Yeah,
yeah, thank you all for joining, and I'm going to give an update on a project that we've been working on here at Green Bank to enable something called cyclic spectroscopy for the GBT. So I suspect that cyclic spectroscopy is probably not a term that everyone is familiar with outside of maybe a group of pulsar astronomers. So what is cyclic spectroscopy in the first place? The kind of high-level definition is that it's a way to take advantage of the periodic or cyclic nature of pulsars to simultaneously achieve both high frequency and pulse phase resolution. And I'll get into a few reasons why we can't do that with normal observing techniques in a little bit. The reason we're interested in this is because cyclic spectroscopy can improve measurements of pulsar scintillation and scattering, pulsar timing, and our understanding of the interstellar medium. So it's potentially a really interesting tool for studying all of those things. So why would we pursue cyclic spectroscopy in the first place instead of just using standard observing techniques? Well, modern spectrometers tend to use Fourier-based methods for actually producing spectra, and time and frequency are Fourier conjugates and therefore subject to the uncertainty principle, which means that using traditional signal processing techniques, you can't simultaneously achieve arbitrarily high time and frequency resolution. Now, in a lot of contexts, that's okay. A lot of spectroscopic sources, spectral line sources, are very, very slowly varying. So you can just accumulate more data and get finer spectral resolution. Pulsars are kind of the opposite. They vary rapidly and can exhibit microscale pulse structure, or even finer in the case of things like giant pulses. But that means that you're limited to frequency resolution using traditional techniques of roughly a megahertz. And that's typically what's used. Now, depending on the science goals, you can trade off a little bit more in terms of time resolution for frequency resolution or vice versa. These are kind of rough order of magnitude for a kind of typical pulsar timing observing setup. But some pulsars do have sub-megahertz frequency structure that we would like to resolve and study. So even though pulsars are broadband continuum sources, there can be features in their spectra that we need to resolve. And so one of the big reasons for this is scattering in the interstellar medium. Multipath propagation through the turbulent interstellar medium effectively causes constructive and destructive interference of wavefronts when they arrive at the Earth. And this causes pulsars to scintillate or to vary their intensity in both time and frequency. When the scattering timescales are long, the individual scintils, as they're often called, which are these kind of patches of intensity in both time and frequency space can be fairly narrow band. And I'm showing here what we call a dynamic spectrum, or the kind of on-pulse intensity as a function of frequency and time, from a recently published paper. And you can see that the frequency scale here is quite narrow. And so some of these features are very narrow band. Now, this is not necessarily the case for all pulsars, but certainly some pulsars can have this type of very narrow band scintillation structure. And so being able to resolve that while also resolving pulse phase is beneficial. These dynamic spectra can be really rich sources of information about the structure of the interstellar medium. One of the fascinating things is that if you take a two-dimensional Fourier transform of those dynamic spectra, you will often see these beautiful parabolic arcs in the conjugate of frequency and time. And these arise due to kind of discrete scattering screens in the interstellar medium. Usually a small number of compact screens actually give rise to the pulsar scattering that we see. And so this tells us something about the structure of the interstellar medium on fairly fine scales. Now, the scattering is both a source of science, but can also be something of a nuisance term, particularly for very high precision pulsar timing. So what I'm showing here is just kind of a breakdown of a noise budget for the nanograv pulsar timing array experiment, where you have different sources of timing noise and the approximate magnitudes and kind of what they depend on, how they correlate. And you'll see midway down the list, there's scattering, also these refraction and lensing terms, which in some cases can be quite small, on the order of only maybe a few nanoseconds, but in other cases can be relatively large for certain pulsars. These are strongly frequency dependent, so they are certainly much stronger at low frequencies than at high frequencies. And in order to obtain the best sensitivity in high precision pulsar timing, it is beneficial to either mitigate this by observing pulsars that just don't exhibit very much scattering, but that limits the sample that you could observe, or by going to very high frequency, but then you lose pulsar flux, or ideally by measuring the scintillation parameters so that you can determine scattering timescales, which are dynamic and vary with time, and correct for them after the fact. And perhaps even using this, be able to time a larger sample of pulsars that you normally would maybe not consider as good clocks because of these types of noise terms. So cyclic spectroscopy can help us both do science and overcome some of these drawbacks of the effects of the interstellar medium. So let's talk a little bit more about what this actually involves. So the cyclic in cyclic spectroscopy refers to the fact that pulsars are cyclostationary, which means that their statistical properties are periodic, as opposed to being time invariant. And this allows us to take advantage of this to produce something called a cyclic spectrum. So the cyclic spectrum, in kind of a quick overview, is calculated by taking a sample-by-sample autocorrelation function of an incoming time series of data, and then folding that autocorrelation function modulo the pulse period. A normal spectrometer would not really worry about the time dimension or do this phase folding, but would merely accumulate the autocorrelation function for different lag values, take a Fourier transform of that, and then obtain a spectrum. But by taking advantage of this periodic nature of pulsar and accumulating different lag products into particular pulse phase bins, we can then take a 2D Fourier transform of that result, and it yields something called the cyclic spectrum, which is a function both of the traditional radio frequency, but now also this other term called the cyclic frequency or cycle frequency, which is related to the shape of the pulse profile in terms of how power is distributed. So the frequency resolution that you get is now no longer limited by the smallest time resolution, but by the amount or the number of rotational periods that you can accumulate data for, and therefore accumulate different lag values for. And the phase resolution that you get is basically limited by your baseband sampling rate. Since again, you're accumulating these lag products into different phase bins by folding them prior to doing this Fourier transform. So that was a very quick overview of the signal processing. Let's talk about some of the benefits. So as I've already mentioned, this allows you to have high time and frequency resolution simultaneously, which means that you can obtain better dynamic spectra for fast pulsars. And on the right here, I'm showing two plots which were provided courtesy of Jacob Turner, who is a graduate student at WVU, and I should say will be starting a postdoc at Green Bank at the end of the summer, early fall. Where on the top is the dynamic spectrum for the original millisecond pulsar, B1937 plus 21, taken with more traditional observing techniques. And then the bottom plot is that same data set, but then processed with cyclic spectroscopy to provide a factor of about 1,000 better frequency resolution. And you can see all of these different scintillation structures emerging there. This is data that was taken with the Arecibo telescope. Cyclic spectroscopy also preserves the phase content of the incoming signal, and that means that you can reconstruct the interstellar medium impulse response function, which effectively is determining what these scatterings, the pulsar scattering looks like. And so that is interesting in and of itself. And in some cases, you can also use that to deconvolve the intrinsic pulse profile and the impulse response function in order to get that intrinsic pulse profile, whereas normally all you see is the scattered version. And so this is data from a paper by Mark Walker, and you can see here that the black is the pulse profile of B1937 plus 21 with traditional processing, and then the red is the reconstructed intrinsic pulse profile. And you can see these very fine features in the pulse profile that normally would not be visible due to scattering. And this is important for pulsar timing because it's these types of very narrow features that allow us to obtain more accurate pulse times of arrival. Another paper by Jacob Turner showed that you also get a more accurate and precise measurement of the scattering timescales when you obtain them from the cyclic spectrum, as opposed to more traditional techniques where you're taking the autocorrelation function of the dynamic spectrum and obtaining the scattering timescale from that. So the top plot here shows these are all from simulations, not from real data, but it shows the recovered scattering timescale on the y-axis versus the simulated and injected timescale on the bottom axis. And as you can see, there's a slight bias there due to signal to noise, but you generally get a much better correlation to the injected scattering timescale than with traditional techniques, which are shown in the bottom panel. And so these can allow you to recover the scattering timescales, correct for them in pulsar timing, and give you better pulsar timing results. So hopefully I've convinced you that cyclic spectroscopy is a really cool and potentially very useful technique. So why isn't everyone using it? So cyclic spectroscopy is implemented in some community-supported software packages, such as DSPSR, but it's very computationally intensive, and it's not generally offered as a standard observing mode. And if you want to process the data in kind of an offline format, then it requires that you record large volumes of baseband data, or reduce your bandwidth to very narrow bandwidths in order to kind of keep that data volume more manageable. And so there certainly are results in the literature using cyclic spectroscopy, but our goal here is to develop a cyclic spectroscopy observing system for the GBT that can observe over wide bandwidths and is easy to use and accessible to all astronomers. And so we have an NSF-funded project to do this, and I'm going to talk to you a little more about the status of that and where we're going in the future. So the original project goals was to enable cyclic spectroscopy over bandwidths of up to 3.75 gigahertz. We were originally setting out to develop an expert user system, but with the goal of full integration into standard GBT observing tools. So this would be a system that, if you're familiar with the GBT, we originally envisioned as not being fully integrated into Astrid, which is our observing interface GUI. Maybe you would have to log into a separate computer to fire up a process in order to enable the cyclic spectroscopy observing modes. We wanted to allow for parallel cyclic spectroscopy and standard pulsar observing modes. One of the important use cases for this is nanograv observing. A nanograv is observing a suite of millisecond pulsars over the course of many years in order to look for very small scale effects of potentially gravitational waves. And so with a data set like that, you want to have a period of overlapping observations in order to verify that you fully understand the observing modes and the data that you're getting, verify data quality. And so there's certainly are results in the literature using cyclic spectroscopy and standard pulsar observing modes. One of the important use cases for this is nanograv observing. A nanograv is observing a suite of millisecond pulsars over the course of many years in order to look for very small scale effects of potentially gravitational waves. And so with a data set like that, you want to have a period of overlapping observations in order to verify that you fully understand the observing modes and the data that you're getting, verify data quality. And so being able to observe with standard and cyclic spectroscopy observing modes simultaneously was an important requirement. And we had originally hoped to be able to process the data in real time. Our approach for doing that was basically pretty naive and to just throw a bunch of compute power at it. So we had a plan of taking the incoming signal, splitting it up into different subbands, processing it with Roach 2 signal processing boards in order to produce a number of coarsely sampled polyphase filter bank channels, and then to send those to a suite of 24 high-performance computers, each equipped with 2 GPUs, which would perform the traditional data processing and cyclic spectroscopy as well before writing that out to a file store. Now, we did some simulations to suggest that this real-time system was computationally feasible, but we had not actually demonstrated that we could do it with the full observing system. We were basically just using a simulated data stream when we originally wrote the proposals. And so we understood that this was a potential risk for the project. And indeed, early investigations with the full GBT system got close to achieving real-time processing, but still fell a little bit short. Luckily, we had planned for this in the original proposal, and we had a contingency plan and a fallback option. So we switched course a little bit. Pretty much everything is the same, but what we're now working on is, rather than a completely real-time system, is to have a system that automatically processes the data in close to real time. Where close to real time here means about a factor of 3 or maybe slightly less than whatever your observing time is. So if you observe for an hour, the data will be ready within 3 hours, kind of thing. And that's the approach that we're taking now. But I'll point out that we haven't given up on real-time processing just yet, but we're focusing on getting something that will be useful and get science out before we go back and try and solve some of the bottlenecks in the real-time processing. So where do things actually stand? Well, with this offline processing approach, we have effectively, instead of adding a bunch of new compute power, added a bunch of new storage to our high performance compute nodes, so that we can record baseband data over 3.75 gigahertz for up to 8 hours continuously. And those disks are now in place and set up, and we have now tested the streaming where we can take data in parallel with traditional processing techniques and record this baseband data to disks. So that's done. When an observing session that wants to use cyclic spectroscopy finishes, these data will then automatically be processed. And we have a system that manages all of that, knows when an observation has started that wants to use cyclic spectroscopy and when that has finished, and fires up the processing systems automatically. And so that's done. We have the expert level control of the CS system enabled, and that's done. And we have some tools for monitoring the data acquisition as well. But things have been going relatively well, and I'm happy to say that we actually are probably going to be able to make this less of an expert level control system and actually integrate it more into our standard observing interfaces than we had originally maybe planned for. So this was originally deemed out of scope, but this is actually progressing relatively well. And so we're currently testing Astrid and config tool control of the CS system just to streamline this and make it easier for observers to use. So you would effectively add a few new parameters to your observing scripts and hit go, and you would enable this observing system. So we have a web interface for keeping track of the data, and I'm just showing some screenshots here. This is still a work in progress and is kind of a development system right now. So it's useful for keeping track of data that's been recorded with the cyclic spectroscopy observing system and what the status of that processing is. But we're probably going to maybe clean this up a little bit, make it a little bit more presentable. But it's a very nice system that takes care of all that. You can see here that when a project has been enabled, it'll tell you what the status is. Here we have one that failed to process, so it recognized that, but others that completed and seemed to be okay. There's one where you can see that the cyclic spectroscopy observing mode was not actually enabled, and so those were logged, but the data are not processed. And we also have, if you dig down, ways that you can try and look at some of the low-level data quality products in order to make sure that everything is working okay. And so we'll have guides for what that should look like, and that'll make it easier for users to verify that their data is being recorded properly. And we have obtained some preliminary on-sky data for several pulsars. So as I assume many people on the call are aware, earlier this year, the GBT was shut down for some azimuth and track wheel repair. So we couldn't move the telescope in azimuth, but we could still tip in elevation. And we were able to do some drift scans of a few pulsars and collect data using the system in that way. So these data, because they were relatively short, just drift scan data, not necessarily of the most use for checking the scientific quality, but were useful for kind of turning the crank and making sure that all of the data collection and processing aspects were working okay. So we took advantage of that shutdown time to do that. Excuse me. And we are now in the process of collecting and analyzing additional data with full telescope motion in order to better assess the scientific data quality. We're currently using that DSPSR package that I talked about to process data, but we are working on a GBO specific implementation. This just allows us to more fully integrate it into our own software architecture, and in a way that our software engineers are more comfortable maintaining long term. We are looking for potential ways to speed up the processing and maybe get back to real time. And that involves looking exactly at where some of the bottlenecks are in the processing, and maybe looking at slightly different GPU cards with resources that might be better suited to the needs of the system. So our default approach has generally been to use gaming GPU cards, but there are some enterprise and data center GPU cards that just have different balance between processing cores, memory bandwidth, that kind of thing, that might be a little bit better suited to what we need. So we're exploring those as well. So as I said, we haven't given up on the real-time processing yet, even though that's not the kind of default that we're pursuing right now. So here's just some simple plots showing the B1937. This is the drift scan data. On the bottom is time running along the x-axis and pulse phase running along the y-axis, so things are kind of flipped. This is just from a few minutes, and you can see that we started a little bit early. The pulsar drifted through the beam of the telescope. We picked up the signal, it peaked in power, and then drifted out of the beam again. So we were only observing the pulsar for a couple of minutes, but nevertheless, we were able to get some good data with that. We have the traditionally processed data on the left, and I've just zoomed into a very narrow range of the overall observing bandwidth that we used. And then on the right, I have data that was processed with cyclic spectroscopy, and you can see the additional finer scintillation structure and frequency structure there. I had to kind of stretch the color scale a little bit, so these data look a little bit noisier than they might otherwise. But again, these were a fairly short integration time. So future work. We are in the process, as I mentioned, of collecting and analyzing more scientific data. So we want to just verify scientific data quality of what's coming out. We're continuing development and optimization of the processing software. And as I said, looking for ways that we might still be able to get back to real-time processing. We are working on automating quality checks and management of the baseband data, and there's also notifications for users. So the way we envision this working is you'll record data. The data will be processed to produce cyclic spectra. There'll be some sort of automatic checks of the data integrity. If those pass, then the baseband data will probably be wiped so that we can record more data on the system, and users will get a notification that their data is ready. And then also just some ease of use improvements, like I said, integrating it into our standard observing system. And so the project is on track to finish in about 1 year, so you can look forward to being able to use the system on something like that timescale. So in summary, cyclic spectroscopy is a really cool technique for providing insights into the structure of the dynamic interstellar medium and improving high precision pulsar timing. And we're on track to deliver a easy to use wideband observing system for the GBT in about a year. And I want to thank the NSF for funding this through a supplement to our cooperative agreement. And I would be happy to answer any questions at this point. Thank you.
Thank you, Ryan, for giving a great update. Participants, go ahead and put your questions in the Q&A box, and we'll go through them. All questions are coming in. One person just said awesome. First question: have cyclic spectroscopy pulsar pulses been observed to exhibit reflection delays from intervening objects or structures similar to a radar signal reflection? Also, can cyclic spectroscopy be utilized with interferometry for the angular resolution to 3D map the intervening ISM structure? So 2 questions.
So in terms of the first question, I'm not aware of anything like that. In terms of the second question, so there's really interesting things you can do with interferometers and observing scintillating pulsars, where you can actually kind of resolve different scintillas in the ISM, and you see these elongated scattering structures. This is referred to as scintillometry, and potentially even use the interference of the signal in the ISM to almost do a type of interferometry. This is where the scintillometry comes in, being able to actually even get information about the physical scale of the pulsar emission as well. As far as I'm aware, that hasn't been done using a cyclic spectroscopy observing systems simultaneously, but I think that there's really interesting potential science to be done there, kind of doing simultaneous scintillometry observations with something like the high sensitivity array, while also potentially using the GBT to record simultaneous cyclic spectra there. So that's definitely something that we're thinking about.
Cool. Waiting. We don't have any additional questions in here now. Do you envision, well, I'll just ask a question. Once this gets going and ready for our general users, and hopefully in about a year's time or so, do you think most pulsar studies observers will move over to this new technique?
So it's
Or they're
not all pulsars are necessarily going to need to use the system, or I should say not all pulsar observers are necessarily going to need to use a system like this. It's going to depend upon the individual pulsars. So some pulsars are not particularly highly scattered, or they show relatively wide band scintillation features, where that additional frequency resolution or the ability to recover that intrinsic pulse shape is not of particularly high benefit. But there are other pulsars that can be very highly scattered, especially at low frequencies. We're certainly interested in using this to improve nanograph timing, and there's a hope that it will become a regular observing mode for nanograv and improve pulsar timing there. And I'm hoping that people will come up with new and interesting ideas for it as well. So I think that it's not going to take over all pulsar observations necessarily, but I think that there will be some really interesting use cases and science to come out of it.
Yes, certainly.
And it's just going to depend upon the properties of the pulsars.
That it's unbelievable, the improvement in resolution. And we have another question that came in. Great stuff. Can you say something about the frequency resolution that you're assuming when you say 3 times real time for processing?
Yeah, so our kind of standard setup is to use roughly 1.5 megahertz coarse polyphase filtering bank channels, and then to sample that by oversample that by another factor of, I think we can get right now to about a factor of 256 better than that, which gets you down to a few kilohertz frequency resolution. So that's what we've been able to do in terms of the 3x processing for right now, in terms of the actual physical frequency resolution for that kind of standard setup. But there's a lot of different knobs you can turn in terms of playing around with the amount of pulse phase resolution that you're getting from that, the actual size of the coarse channels that you're doing. And so we're looking into still adding additional GPUs, maybe being able to expand the parameter space that we can do that 3x processing for. But that's kind of the baseline right now. We've been aiming for about a few to 10 kilohertz resolution. We can achieve that, we know that. And so other things are going to be a bonus on top of that.
Great. Waiting for any additional questions that'll come in. As we wait, I'll just throw in a question. Maybe I could do this off. Oh, we have a question. This is good. The question is, do you have any issues with the effective signal to noise ratio as the resolution is made finer, and understanding how much of the structure is real? If so, does the repeatability of pulsars allow you to add many instances of the pulse to overcome statistical fluctuations and improve the overall signal?
Yeah, so the time scales over which you would want to kind of average or sum up the data are depend upon the not the scattering time scale, but that scintillation time scale. So remember I said that you get these kind of bright patches in both time and frequency. And so as the pulsar and the Earth, which are moving through the ISM, you get different lines of sight through the ISM, you get different scattering properties. As that changes, eventually things kind of decohere, and you want to limit your observing time to something like, generally it depends on the pulsar, but maybe like a few minutes or something like that. So that's one way to build up signal to noise. There is signal to noise issues when you're looking at individual channels like that. So if you overchannelize things too much, then you'll have low signal noise in any given channel. And so certainly brighter pulsars are going to be it'll be more useful for that than extremely faint pulsars. And I would point you to a paper by Tim Dolch that explored a lot of this parameter space in terms of developing kind of like a figure of merit for when cyclic spectroscopy will be useful for doing things like recovering the transfer function and that type of thing.
Great. An additional question, can cyclic spectroscopy provide additional information about pulsar glitches?
Oh, that's interesting. I haven't actually given much thought to whether or not this would be useful for gaining insight into glitches. Glitches are related more to the intrinsic properties of the neutron star themselves, as opposed to interstellar medium effects. So nothing immediately comes to mind, but if people have ideas for how they might want to use something like this, I would be happy to hear about those.
Okay, I'm going to ask my question in terms of long term. Are you planning of having different types of modes, like you'd have like different Vega spectroscopy modes, but for cyclic spectroscopy configured for different whatever resolution or timing?
Mm-hmm. Yeah, so the system will be flexible in terms of what you can specify in terms of kind of processing times. And if we get to real time, the limitations of what we can do in real time, there might be some limits that are more practical in that sense. But the system will be it'll be easy to specify different combinations of initial channelization and cyclic spectroscopy channelization just through the standard observing interface. And so there'll be many different combinations there.
Great. Another question, would cyclic spectroscopy be useful for studying giant pulses?
Yeah, so one of the things about cyclic spectroscopy is you're getting the high resolution and pulse phase, but you're still accumulating data from many different rotations into different pulse phase bins. So in terms of resolving an individual giant pulse, I think that still very rapid sampling of the incoming data stream is going to be better for that. But maybe in a statistical way, I'm trying to think if if the giant pulses are coming in particular phase bins, then you might be able to accumulate a number of giant pulses into particular phase bins and still see some structure, again, averaged over many pulses there.
Okay. I think that's going to end it for our questions for today. So thank you, Ryan. And if people, somebody asked for repeating FRBs. Do you want to say anything? We'll make this the last.
Yeah, that's a similar thing there. So, if you found an FRB that was periodic on relatively short time scales, then you might envision doing something like this. But over the time scales of many minutes, many hours, that kind of thing, you're not typically folding the data in that sense to produce a cyclic spectrum. So
okay, well, thank you, Ryan, for giving your presentation today and giving us an update on the status of this project. If people have questions for Ryan, feel free to contact him offline. So thank everybody for listening. And our next community Zoom, I assume it'll be in 2 weeks. And I apologize, I don't have the webpage up to know what to advertise the what's in 2 weeks, but an email will go out about that. So thank you, everybody, and have a great day.